Hello guys, in this video we'll be discussing the complete introductory details of moment of inertia, that what is moment of inertia, what is its physical significance, how do you imagine the moment of inertia, and on what factors does it depends, is it a vector quantity or is it a scalar quantity, and its formula. So these all important details would be discussed in this video, and we would be discussing the formula for calculating the moment of inertia of discrete mass system also. So what is moment of inertia? So moment of inertia is an inherent property of a body which can rotate, obviously, and by virtue of this property, that body resists any change in the state of its rotational motion. Now it means that let us, if we discuss the second question, that how can I practically imagine the significance of moment of inertia. So it is very difficult to stop a helicopter wing manually, but it is comparatively easy to stop a fan blade which is rotating at the same speed, because the helicopter wings has a very high moment of inertia, and therefore it would oppose any change in its rotational motion state. So there would be a huge amount of force which would be required to stop that helicopter wing, as compared to the force which is required to stop the normal fan blades, if they are rotating with same speed. So the greater moment of inertia of any object, and the greater would be its resistance either to come to rest from a rotational motion state, or to start the rotational motion from the rest state. So this is just like the inertia, and the inertia was the property which resists the change in any state of motion, but specifically moment of inertia is the inherent property which resists the change in state of rotational motion only. Now the factors on which this moment of inertia depends are the mass of the object, obviously. Moment of inertia also depends on the inertia. Now it depends on the distance of that object from the axis of rotation. This is very important, that as this moment of inertia is associated with rotating bodies only, therefore this moment of inertia depends on the radius of circle in which the object is rotating, or its radius of gyration. Now it also depends on the shape, size, and the axis of rotation of the object. So these are the factors on which moment of inertia depends. The formula which is experimentally derived of moment of inertia is I is equal to mr square, where m is the mass of the object and r is its distance from the axis of rotation. So this is the general formula for the moment of inertia of any rotating object. Now, is this formula of moment of inertia will be the same for any axis of rotation? No. The formula for the moment of inertia of a body, of a same body, will depend on which axis of rotation is it rotating. So the formula will depend on the axis of rotation, and if the body is rotating on a different axis of rotation, about a different axis of rotation, its moment of inertia formula would also be the different one. So does moment of inertia depends on the density of the object? Yes, obviously the moment of inertia depends on the density, and in fact the formula for moment of inertia of two objects of same shape and same mass is different if one of them is hollow and one of them is solid. The best example of this question is the case of solid sphere and hollow sphere. The solid is, if we take a solid sphere and a hollow sphere of same mass, same radius, and they are rotating about a same axis, or we can say a common axis, then the formula for moment of inertia for both of them would be different, because their density is different. So yes, moment of inertia depends on the density of the object. Now, is moment of inertia a vector quantity or it is a scalar quantity? Actually, moment of inertia is neither a vector quantity and it is not a scalar quantity. In fact, it is a tensor quantity, because sometime it depends on the direction of rotation and sometime it depends on the distribution of masses around the axis of rotation. So if it is depending on the direction of rotation, then it is a vector quantity, and if it is depending on the mass distribution around the axis, then it is a scalar quantity. So combinedly it is a tensor quantity. Now moment of inertia of a discrete mass system can be easily calculated by summing. This is summation of mi ri square I is equal to 1 to n. This is the complete moment of inertia. What I mean to say can be explained by this example, in which there is a system which contains n number of masses which are individually separated by a distance of r1 from the common axis. R1 is for m1, r2 is for m2, and similarly for the ith mass it would be ri. So it doesn't matter that the masses are distributed on the either side of the axis or they are distributed on the same side. The moment of inertia of the masses would be m1 r1 square plus m2 r2 square plus m3 r3 square up to mi ri square. So this is the formula for moment of inertia of discrete mass system. Now in this let us take some questions. Now in this question there are two particles of masses m1 and m2 which are situated in the plane which is perpendicular to AB, and the distance of m1 from the axis of rotation is r1 and the distance of m2 is r2. So we have to calculate the moment of inertia of the system initially. So for the first question, the value of moment of inertia would be m1 r1 square plus m2 r2 square. This would be the value of moment of inertia. Now we have to find out the moment of inertia of the system about an axis which is passing through m1 and perpendicular to the line joining m1 and m2. So let us draw an axis which is passing through m1 and it is also perpendicular to the line joining m1 and m2 to this line. So the moment of inertia of the system about this axis would be I is equal to m2 into r1 plus r2 square. Because the moment of inertia of m1 would be 0, because this axis is passing through m1 itself, so the distance of m1 from this axis would be 0, and hence the moment of inertia about this axis would be the moment of inertia of m2 only, and m2 is situated at a distance of r1 plus r2 from this axis, so its moment of inertia would be m2 into r1 plus r2 whole square. Now in the third part we have to find out the moment of inertia of the system about an axis which is passing through m1 and m2. So we have to find out the moment of inertia about this axis, this one. So if this is the axis, so the moment of inertia about this axis I would be 0, because again this axis is passing through both the masses and their distance from this axis would be 0. Now we have to find out the moment of inertia of this system about an axis which is passing through the center of mass and perpendicular to the line joining m1 and m2. Now there is an axis which is passing through center of mass. Now we have to first of all locate the center of mass of this system. So if this mass is m1 and this mass is m2, and the distance between them is equal to r1 plus r2. Let's suppose that this distance is equal to r. So we already know the distance of COM from the first mass x would be equal to m2 r upon m1 plus m2. and let's suppose that this distance is y. So y would be equal to m1r upon m1 plus m2. So so moment of inertia of the system about COM will be m1 x square plus m2 y square. Okay, so if there is an axis which is passing through COM and which is perpendicular to this axis, so this axis would be coming out of the plane, and the center of and the moment of inertia of the system about this axis would be m1 into x square plus m2 into y square. So if I substitute the values of m1 and m2, so this is in fact x and y. So x is equal to m2r upon m1 plus m2. So this is m2 square r square upon m1 plus m2 whole square, plus this is m1 square r square upon m1 plus m2 whole square. Now ICOM would be m1 m2 upon m1 plus m2 into r square, and this we call as reduced mass. So we can directly write down the moment of inertia of a system about their center of mass for two mass system by using the concept of reduced mass, and we can directly learn the formula that reduced mass is equal to m1 m2 upon m1 plus m2. Now in this case you can see that there are 3 or 4 axes. This is axis number 1, this is axis number 2, this is 3, and the 4th axis is passing through this center and it is perpendicular to the plane. So we have to find out the moment of inertia about these 4 axes of this system. So first of all, the moment of inertia of the system about this first axis. You can see that this first axis is passing through this mass m and m. So the moment of inertia of m and m would be 0, but the moment of inertia of this m and this m would be non-zero, and the value of moment of inertia for each one of them would be same about this axis 1. This distance is x, so x is a by root 2, because the half of the diagonal of the square is equal to a by root 2. So I1 will be equal to twice of the moment of inertia of any one of them. So the moment of inertia would be m into x square. So I1 would be equal to twice of m into x, whereas x is a square by 2. So I is equal to ma square, I1. Now the moment of inertia of the system about the axis number 2. So about the second axis, you can see that the second axis is not passing through any one of them. So the moment of inertia of all of them would be non-zero, and therefore you can see the distance of all the masses from this axis is same, which is a by 2. So we can write down that the total moment of inertia would be 4 times to the moment of inertia of any one of them. So the moment of inertia of this mass is m into a by 2 square. So I2 will be equal to ma square. Now the moment of inertia of the system about third axis. You can see this axis number 3 is passing through these two masses. Therefore the moment of inertia of these two masses about this axis would be 0, and the moment of inertia of these two masses about this axis would be same and non-zero. So this is twice of moment of inertia of any one of them. So the moment of inertia of this mass about this axis would be m into a square. So this is 2ma square. And I4. I4 is the moment of inertia of the system about this axis which is passing through the center. So you can again see that all of the masses are situated at a same distance of a by root 2 from the center axis. Therefore, the total moment of inertia would be 4 times to the moment of inertia of any one of them. So I4 will be 4 times m into a square by 2. So I4 will be equal to 2ma square. Now let's move on the next question. Now in this question you can see that this system has 3 masses m, m and m which are placed on the corners of a equilateral triangle, and there are 3 axes. This is 1, this is 2 and this is 3. So we have to find out the moment of inertia of this system about these 3 axes. So the moment of inertia about the axis number 1, which is this green axis, and this green axis is passing through these 2 masses, therefore their moment of inertia would be 0, and the moment of inertia of this mass about this green axis would be m into h square, where h is this distance. Now this distance h is equal to root 3a by 2. We all know that. So the moment of inertia of this mass would be m into h square. So I1 is equal to m into 3a square by 4. So I1 is equal to 3ma square by 4. Now about axis 2. So about axis 2, this axis 2 is passing through this mass, and therefore the moment of inertia of this mass about this axis is 0, and the moment of inertia of these 2 masses is same about this axis, and the distance of each one of them from this axis is a by 2. So this is twice of m into a square by 4. So I2 will be equal to ma square by 2. Now the moment of inertia of the system about I3. Now third axis is this one, and this is passing through this mass. So the moment of inertia of this mass about this axis would be 0. But the moment of inertia of this one about this axis would be calculated by this distance, which is a by 2. So this is ma square by 4 plus the moment of inertia of this mass about this axis will be calculated by this distance. Now this distance is a, so it is ma square. So I3 would be 5 by 4 ma square. So this is the complete analysis of discrete mass system moment of inertia. Thank you.